Okay. Good morning to all that are in person, and also good morning to those that are online. Just before I start, can I say again for mobiles to be on silent, please, or switched off? That'd be great. Thank you. Yep, we had those that attended last night will obviously know how successful the evening was at our Next Gen Awards. There were some fantastic prizes that were awarded that are showing on the screen now. So and some people will not know who won the awards. It was an incredibly hard process to actually to designate who got what award, because there was lots of nominations, and we also found it hard to choose. Because they were all equally deserving, and not just the award winners, it's the whole Next Gen team for the successful work that they've done since they were incepted about a year ago, I think. So a big thank you to everyone on the Next Gen team. But in terms of who won the awards, it went to the EC, who voted from the nominations. So on the screen, you'll see that the Engineering Excellence Award went to Thank You Target of Vodafone, and the prize is a 1,000 ESCA training bursary. Whatever training they feel that they want, they just approach ESCA, and we will make a £1,000 bursary. For scholarly achievement, Xenia Zimmerman of BT, again a 1,000 ESCA training bursary. For industry impact, Chloe Morris, Ocean IQ, a great prize sponsored by Suboptic to attend the event in Lisbon in June, which also comes along with a travel bursary as well. So a fantastic prize for that. For environmental awareness, Quina, sorry if I mispronounce your name, Quina Nguyen from OEC, £1,000 ESCA training bursary again. Project contributor, Anna Bladen from Briggs Marine, another fantastic prize from ICPC for travel and attendance at the ICPC plenary in Montreal, Canada. Fantastic prize. And for innovation catalyst, James Wickham from Vodafone, and another £1,000 ESCA training bursary. So congratulations to all those that got the awards. But again, as I said, congratulations to the whole Next Gen team. So a round of applause for them, please. The thing with the award winners is that they can't win next year. So next year there'll be different award winners. So but yeah, congratulations to everyone. Just for those that never attended yesterday, just a reminder that we did hand out some lovely notebooks and some lovely tea towels with disorder map printed on them. So for those that are not here yesterday, if they want to come to see me, I'll let you have the pen, the tea towel, and the notebook. So moving swiftly on to today, and first agenda item under the category repairing cables when they're damaged, power cable repair from Dave Sutherland, National Grid Ventures.
Can you just press that on? Yeah, that's fine. Does that work?
slides probably. Yeah. There we go.
Is working there?
Yeah.
Brilliant. Yeah, hi everyone. I spoke yesterday briefly about sort of siting and routing, and today you get to hear me talk about one of our recent cable repairs. So this one is on the IFA2 cable. This is an interconnect that runs from Portsmouth to France, and half of it is owned by National Grid Ventures, and the other half by RTE, which is the French equivalent. It's quite a long cable. It's not the longest of ours by any means, but it's still a couple of 100 kilometers, and the responsibility in terms of permitting, because that's my area of expertise, the area of permitting is also split along the EEZ. So the cables in the UK waters sits with me, and the other side sits with RTE. And the fault occurred in November 2023. There was an outage, and the bottom map up there shows roughly where it is. Possibly one of the busiest areas to have an outage outside of the Thames estuary. So we have fishermen, got the military in the Portsmouth Harbour, we've got Southampton Port as well. So it was a really, really busy area. And on top of that, it is also a special area of conservation, special protection area. But this gives you an idea of the jurisdictions and the permits that we need, and we'll come on to those in a little bit. But that shows where the IFA2 fault location is, sort of where we have to apply for permits and who's responsible for it. So we don't have to deal with anyone onshore because it's below mean low water springs. We do have to talk to both the MMO and Natural England. The MMO because it's we have a license on our cable, and Natural England as well. Talk to them quite a lot because it's in this marine protected area. And that's a sort of cut through of the IFA2 cable. So it's got two poles and then a fibre optic cable as well. And the cables are sort of banded together, and it is more complicated to retrieve than perhaps a single fibre optic telecoms cable. So these are some pictures of the vessels that we used. I think there's some more pictures a bit later on. But because of where it was located in this sort of conjunction of all the shipping lanes and ferry lanes and fishing grounds and everything else, we had to go and talk to the various harbour masters and vessel traffic schemes. King's Harbour Master in Portsmouth was very helpful with this. They agreed to issue their local notice to mariners and just asked to be kept informed of the works. We did have a slight hiccup when the connector on the bottom turned up, and because of its size required a pilot, and the harbour master was like, we don't have any pilots. So we were sort of scratching our heads for a little bit, and I think they got some possibly out of retirement to come and help sit on the boat for a bit. But that was an interesting start to it. Got off on slightly the wrong foot, but we got there in the end. Then the Crown Estate, all the power cables have a seabed lease. And you'll have heard from Morris and the Crown Estate yesterday that generally your consented corridor is sort of 200 plus meters either side of your centre line. And your repair works pretty much have to lie within that. Normally it's not a problem, you're just cutting the cable and then rejointing it and laying the loop, but you just have to make sure that that loop sits within your consented corridor. And then the last one was just the MMO. There's a selection of permits that are required. So typically, traditionally, you can pick up, recover your cable, you can repair it and relay it. Just under exemptions, you don't need a full marine license, but should you wish to protect this cable, you need a full marine license, for which the statutory timescales are, I think, 13 weeks, but in reality, it takes a little bit longer to get. So, we did that. We sent them in, sent all the exemptions in, and then ran into winter. So terrible weather. All the exemptions were submitted again, and possibly again. I think we ended up sending quite a few. So the way the fault location and everything works, I'll come to that in a little bit. Basically, every step needed an exemption or a permit. Got them all in. It's fine. It was just you had to keep sending them in. Send in another one. Oh, why are you sending another one? Bad weather downtime, things like that. Things you can't control. But we got them. Those are some of the cables coming on board. That's a multi-beam scan at the bottom of the cable, and I think one of the rock berms near where we were like deburying the cable. And then there's a sonar image of the trench from one of the ROVs that was down on the seabed doing it. So this is a very high level overview of how we fixed the cable. So we located the fault. Don't ask me how they did it onshore. As far as I'm concerned, it's black magic, but they got a rough KP range and said, right, we think the fault's within this and this area. Then did an offshore survey. So we had a couple of survey boats out there. And you might remember yesterday there was a picture of, I think it was Matt's presentation, where there was a yellow ROV with a black frame on the front, TSS. They did a couple of surveys to try and find the fault and confirm the location. The last thing you want to do is cut a cable in the wrong place when it costs upwards of £500,000 a kilometre. So you find the location. Pretty sure you know where it is. Give yourself a bit of wiggle room on either side, and then we end up submitting a sort of final set of permits to cut it, debury it, and all the rest of it. So in UK waters, our marine licence generally stands to say that you have to bury our power cables to 1 metre. It can vary in other jurisdictions, but in our UK waters, it's 1 metre usually. And if it doesn't make 1 metre, you'll have a rock there, usually on top, which the previous slide showed you that image. So the particular location we were at was just, they wanted to cut it, I think it was like a couple of metres into the rock berm. So we removed the rock and then started deburying the cable. So we used divers and an ROV jetting tool to debury the cable. The jetting tool to do that. The next step, the divers with the cutting, and they also used an ROV cutter in the end as well because of the level of armouring on the cables. The cables were then brought back on board. Again, you're lifting quite heavy sections of cable, and again, as I think it was mentioned yesterday, the boat has to stay stationary while it's doing the jointing. So we had a very long, very large vessel parked basically in the middle of the Solent with things going around on either side of it. And that was there for quite a long time while they fixed the joint, tested it, and then they had to come to relay it. And the way they ended up relaying it, because once you pulled it up, you can't relay it in the same straight line again. You have to put in a loop. And again, I think yesterday we touched on the minimum bend radius from the different cables. There's a slide up that spoke about like fibre optics have a minimum bend radius of 1 or 2 meters. And big power cables looking at sort of 5 meters before it turns around. So you put it back down. There's a big loop round, and when you're sort of laying the cable again, you can put it back in the same trench. The advice from Natural England, because they are usually not in favour of cable protection. You know, we heard that yesterday, particularly in marine protected areas, is to basically go deeper and try and lower the cable as much as you can. So again, the large picture there, mass flow excavator. We did a couple of passes with that to try and lower the cable, but you end up it becomes less effective the more times you do it. So the first time you do it, you can get quite a large change in depth, and then it gradually gets less and less as all the mobile sediment is sort of removed. But we didn't quite get it far enough down to make the engineers happy or to meet our marine license requirements. So we ended up having to get a full marine license for cable protection. So this is a very convoluted timeline, but basically trying to fit it all onto one slide. It starts off like where we get the outage, like when the vessel started mobilizing, how they found it, some of the surveys, cable cuts. There's a diver going down in a cage on one of those. Glad I wasn't him, given it was in the middle of December. There's a picture of the cutting tool, I think, there as well. And then once the cable was relayed, we had a guard vessel on site. So this is to warn off fishing vessels, to warn off other vessels in the area. They got a little bit excited and I think told one of our Navy vessels they had to keep a nautical mile away from our cable. And the naval vessel very politely pointed out that in actual fact that would put them on land if they kept that far off. But it was fine. We had an interest. I think the the colleagues in Ops had an interesting call from the King's Harbour Master on that one. It's like, rein it in, tell them to pipe down, they're just there to protect your cable. But they've done a good job, but they have been there since about January last year. Our marine license application went in shortly after we'd finished the cable, because one of the concepts is that you have to know exactly where you're putting your rock down. But that doesn't sort of stop the repair and the relay and the sort of return to service. So the cable went back into service in February, end of February. And then just after that, the last one, got our license application submitted, and then we got it in November last year. So this is just a rough outline of how long it took. So it took us 99 days from when the outage first happened to getting it back into service. So just shy of 100 days, which was quite good given it was over winter. We had to sort of get spares in from France. We had to get numerous different vessels, some of them fairly specialist at quite short notice. So yeah, so this is again, it's a multi-beam picture of the Omega loop. So you remember I said you can't just lie it straight back in line. That loop up and down is very roughly about 70 meters, up 70 meters, back down, around that sort of length. And you can see this was done with a mass flow excavator. So you can see it's cut a trench into the seabed, it's moved the sediment off. But because it's been moved off, we then have to protect it, because we essentially moved the sediment away, and we wanted to protect it as soon as we can, because having spent upwards of £30 million to fix it, we want to protect it. It is a very heavily fished area. We've had some interesting conversations with fishermen in the area, because this particular area is very, very key for scallops, apparently. It's just this bit. Yeah. And we've had fisheries liaison officers who have gone out, they've done port tours, they've sort of explained, you know, why they can't fish over it, why there's live cables. And again, we heard yesterday, different types of trenching will result in different types of, like, I guess, how narrow your trenches. And the excavator tends to leave quite shallow trenches. So if they were trawling with their scallop dredges, with their prongs in, they would catch the cable. It's not good for anyone. So anyway, it was all done. The FLO went around the ports. We had a couple of chats with them. I think they were begrudging acceptance, should we say, that we're there until we're there. Anyway, got the license. Fantastic news. We're now trying to get a rock placement vessel, which we can't get until we get the marine license, because they're very expensive. And we don't want to sat around waiting while we try and get our marine license. Yeah, that was it really. But because it's such a short distance, it's very hard to get a vessel of opportunity. It kind of has to be in the area, because it's about half a day's work, if that, to put the rock down. I would say, despite the location of it and it being in a marine protected area, we're talking to Natural England worked really well. I mean, it was only designated for seabirds, this area. It wasn't designated for marine habitats, which made applying to put rock down better or easier. And we got there, right? So it was a success. But one of the things that we were sort of highlighting was, there's been in the news recently, there's been lots of stories about, in the Baltic mostly, cables being cut or damaged. There's a list up there, but there's the two pictures that look with the black redacted top secret information on. They're from one of our cables that were taken late last year. One of them, bottom left, deer carcass, weirdly, on a rock berm, which we think was lobbed on by some fishermen to attract crabs and lobsters. Yeah, fine. They've done well to just kick one of those over the side and have it land square on a rock berm. The other one on the top right is a fishing pot touching the cable. So these are the sort of things this is why we want to put rock on the cables to stop stuff like that happening. But yeah, hey, we got there. I think the main finding of it was there was a preference from higher up, shall we say, that we get faster sort of cable protection. Once we sort of repaired the cable, done all the work, and the vessels were cleared off. Yeah, mainly to stop damage like that happening, or to stop the risk of things snagging, or people lobbing dead deers onto the cable. But that's it. That was the eye for 2 repair.
Hi, Dave. Thanks for that. Very quick question, probably technical, so I don't know, maybe somebody else in the room might be able to answer. But you said on a couple of occasions there, obviously you can't put the cable back where it was before in a straight line.
Yeah.
Why not?
I'm gonna let Matt answer that one. He's trying to hide.
So if you've lifted the first joint, you have 2 joints in a repair because you're having to stitch a new bit into the place where you had the broken bit. So you've cut out the broken bit and the first end you joint in, you do lay back a straight line. But the problem is that the cable in a straight line on the seabed and you've had to lift it up to the surface means you've got extra cable length needed to bring the cable up to the surface. The water was, say, 20 meters deep, which means you need to have 20 meters up and 20 meters down. The rest of the cable will be lying on the surface while your repaired bit is on the ship. So you end up with an extra 50-ish meters of cable that you've then got to lay down because there's 20 meters of water. You can't cut that off. No. the joints have to be done on the back of the ship. You can't do the joints subsea. If you could do the joints on the seabed, you have straight lines, and people have thought about doing that. But for all the repairs, they're done on the ship, which means you have the water depth cable twice of loop to lay down, plus whatever amount of cable you need to have on your ship, which is normally at least 10 meters. So that's why you've got, in this case, 25 meters of water, roughly 60, 70 meters of loop.
Yeah, what Matt said.
Richard, we might have any questions.
Quick question. Root cause of failure?
I'm not sure I'm allowed to say at the moment.
Well, quick answer.
Thank you.
Okay, thanks, Dave.
All right.
Next presentation, Sally with Global Marine on the telecoms cable.
Thanks, Clive. Morning, everyone. Yeah, so quick introduction. My name's Paul Staley. I'm mainly involved with management of telecoms repair operations in the Atlantic, covering all around Western Europe, the Atlantic, Caribbean, South America, going some of the way down West Africa as well. So I think perhaps telecoms is going to look a little bit easier after Dave's presentation there. Kind of glad that I'm in telecoms, having seen that. So as we all know, demands for bandwidth have just increased exponentially over recent years. We're using internet all the time for everything pretty much. So networks operate 24/7 all year. They're usually sold with some sort of contractual kind of obligations in terms of availability. So to meet those requirements, protected by diverse and resilient routings to ensure that availability, and also all the route planning that we saw yesterday, all goes towards kind of trying to avoid issues in the future. However, they do fail. As we saw, there's often not always a perfect route. So you're always going to be in areas of danger potentially. So when they do go down, and this is where it differs from power, it tends to be a very, very quick process of getting the ship out there to repair it as quickly as possible. To achieve this, there's maintenance contracts in place covering the 3 main areas of the network. So it's backhaul, the front haul, and then submarine, which is basically beach manhole to beach manhole, which is what I'm going to be covering today. So in terms of faults, obviously they're highly engineered, complex products, subsea cables, but they are operating in a difficult environment. As we know, basically anything man-made doesn't really like salt water, especially salt water that's constantly moving around with things being dragged through it. So the main causes of faults are external aggression or human interactions. So that's fishing activities, mainly bottom dredging, and also ship's anchors, whether that's people dropping anchor because they don't know the cable's there, or dragging that anchor accidentally. How do we know what's caused those faults? There's often evidence, either from kind of virtual evidence from AIS tracking of vessels. You can see they were there at the time the cable went down. So you have quite a precise kind of estimate of when that cable faulted and can put a ship there at that time. In terms of fishing, you may see evidence on the seabed, so see trawl scars. You will find fishing gear still attached to the cables often when you bring them up. If you're lucky, it might have the name of the fishing vessel on it. And then moving on to ship's anchors, again, you've got AIS to monitor that, or if you're really fortunate, as you can see from the top right there, you have the anchor left there with the cable wrapped around it, and the ship's long gone. So you couldn't get it back up, so just left it. Just going back a little bit, sorry, there's three different types of faults. Optical faults tend to be the easier ones to find. Electrical shunt faults, which, as Dave said, bit of a dark art in terms of testing for that, and generally not so easy to visually identify. So the fault on the top left would be a shunt fault. You imagine if that's on the seabed, some sediment on it, you're not going to see it. You have to detect it somewhere. So moving on to the causes, the geological natural disasters, obviously that would depend on the region quite a lot. You can have earthquakes, which cause faults through either the seabed movements or turbidity currents, which we'll come on to. Hurricanes, again, that could be debris swept out by the hurricane, or see extra swell, that kind of thing, acting on the cable. Undersea volcanic activity, again, I think somebody mentioned the Tonga volcano yesterday, can take out cables. And then turbidity currents, which is something we seem to be seeing a bit more of recently. And that's basically where you've got mass outflows of sediment coming down in the seabed canyons, and can take out multiple cables at one go and leave them deeply buried. So very difficult to find and repair when those ones happen. The last few, not so common, sort of design and manufacturing and workmanship. Those ones are probably the ones we see least, thankfully. So everybody's good at their jobs. Abrasion currents we see quite a lot. Again, that's kind of regional, depending on where it's laid and seabed type. So you see a few in the Gibraltar Straits and other areas around the world. So how are they repaired? As I mentioned, most cables are entered into maintenance agreements, and there's two types of those. So you have the zone agreements like ACTA that I work on, and private agreements like APMA, covering similar areas. They provide access to cable repair ships that are on call 24/7. So they're fully manned 24/7, fully stocked up with food, water, fuel, ready to go out for 30 to 40 days at a time if needed. The agreements also provide scope for storage of spare cable and repeaters, kits, and that kind of things at depots, sort of strategically located depots around the world. And cable ships tend to be located at these depots as well, so they have quick access to those spares. Chart on the right is just showing the kind of the zone agreements around the world. You can see this, it covers most of the ocean, certainly where there's cables. And there is a little bit of overlap there in reality. It's not quite so clearly delineated. So moving on to the cable depots, this one's in Portland down the road. Just to give you an idea of the scale of that, the ship on the left is about 131 metres long. The ship on the right is about 138. So you can see it's a big facility and it's storing a lot of cable in there. Just while we've got the picture of the cable ships, I just say to anyone here, if you ever get the opportunity to go and see one, then please take them up on that, because it's what really does put the industry into perspective. Once you see that, you can see what goes into laying and repairing cable. So here's a look inside that depot. You've got indoor cable tanks. Another alternative at other depots around the world is outdoor cable tanks with suitable covering over the top. Repeaters and other optical bodies are stored in the kind of the metal frames you see there. I think there's one set up at the testing. And then the jointing kits, which we'll come on to, are stored just mainly on pallets of kind of flight cases, as you can see there. So what happens when a cable does fault? First of all, an alarm will go off at a different kind of knot to where we are now, so network operating centre. NOC operator will advise the terminal station, will call out an engineer to go and test that. Usually at that point, someone will phone somebody like me to give us a heads up of a potential fault so I can start gearing up the ship, even though they're ready to go. It's good if they can have a little bit of notice. It can generally get them moving quicker when that becomes definite. So I think me and Richard were laughing last night about the surprisingly calm phone calls we've had at 3 o'clock in the morning when things do go wrong. But yeah, everybody kicks into action and kind of goes through the process. So at that point, the test engineer will go and investigate the fault using optical and electrical techniques to try and pinpoint where that fault is, as that's kind of crucial information at that point. Or if they confirm it's in the marine section, again, absolutely crucial they get it in the right place, because you don't want to send a ship out and it's not in that area. So at that point, repair vessel will be mobilised, and generally, if there's no permitting involved, it can go out within 24 hours. But I think Andy's going to come on to that later, that there are delays due to permitting. So that's probably the main driver of that kind of initial timescale. As part of that, the customer, the cable owner, will give a fault distance, translated into geographical location. That will determine what spares to load and various other parts of how the repair will be done. So the ship is mobilised, it's headed out to site, however far that may be. The first step, if the repair is in shallow enough water, you can locate the cable using various techniques like ROV survey, electroding to try and cut, especially for shunt bolts, that's especially useful. If you're in deeper water, then unfortunately it's a bit of a shot in the dark. You've got a route position list which tells you where the cable should be, but you are literally just hanging big hooks over the back of the ship trying to catch that cable. It's given an idea of timescales on that. If you miss one of those grapnel drives, then you can be looking upwards of it up to a day. So it can go on that part if you're not lucky enough to catch it first or second time. So at that point, you've located the cable and hopefully the faults as well, so you know exactly where it is. If it's not cut already, then you need to cut the cable, as we were just talking about. You've not got enough slack in there to be able to bring the cable up to the surface, so you have to cut it first, bring one end up at a time. So you bring your first end up, recover that with grapnel or ROV, remove any damage there, test it to make sure there's no further faults further down the line, and then you buoy that off so you can go and get the other end. So you can repeat the process there, and then by that point you know what distance you've got between the two locations. You can calculate that final bite size based on depth of water and cable that needs to be on the ship and for jointing. So you pick your replacement cable, joint onto one end of that, and you lay that out in a straight line towards the buoyed off other end. You pick up the buoy, bring that on board, and then you kind of balance the ends and calculate exactly how much you need at that when you cut the spare cable to be able to join together. Once you've done that, so you've jointed the final two ends together, you end up with what we call the final bite, which is that kind of omega shape, hopefully, that you lay out from the ship, so the ship moves away from the cable line, paying that out, and eventually releases it to the seabed, say in a lovely omega shape, if all goes to plan. After that, if it's deep water, then you just leave it. There's nothing you can do. You can't see it. You can't tell where it is. So the ship would, after testing, the ship would be released by the cable owner and head back to port. If it's shallow enough, then they can do an ROV inspection to see how well that is laying on the seabed, making sure there's no loops in it or anything like that. And then if the seabed allows, they can rebury that cable. So, again, we've got a short animation just to show you that in practice. Right, so I've forgotten about the overly dramatic music accompanying that. But anyway, gave my voice a rest. So moving on. So sometimes the fault can be within the marine section, but it's not within an area that's deep enough for the cable ship to work. So generally, cable ships can work into around 10, 12 meters, depending on various factors like weather, seabed type, and that kind of thing, and sort of any obstructions nearby. So at that point, you have to come up with a different solution. There's kind of two ways you can do that. You can repeat the process that Richard explained yesterday of installing a new shore end. Obviously, you've got to kind of pick up the one that was there as well and joint into the existing cable. You can see on the right there, just the line of floats going from the ship to shore. And then those floats have got the cable suspended underneath them. Those floats will be cut away and the cable will sink down to the seabed. The other option, which you use maybe if it's a really long shore end and too long to be able to do that technique, is to use a dedicated shallow water vessel and go and kind of repair it in situ. That could either be a purpose-built vessel or something just available locally, like a jack-up barge. I think that one there on the left was just a local kind of research vessel, which happened to have a good bit of back deck space and winches and things that came in useful. So moving on to kind of what it all comes down to, which is the little joint at the two little joints at the end of it. This is a really specialised skill with highly trained jointers. Most cables utilise what's called like a universal jointing technique, but the only universal bit about it is the common component kit you can see in the middle there, and the outer protection kit. And where there's so many different cable types, they all have different end specific kits. And jointers need to be trained in all the kind of cable types they might encounter in the area that ship operates. So yeah, there's a lot of knowledge there. See, steady hands required, and it's what it all comes down to. And a lot of pressure on those guys when it comes to it. The ship's gone through a lot of work to get to that point, in finding, recovering the cable, and then it's down to sort of 4 or 5 people in a small room, kind of putting it all back together, hopefully. I think that's it from me. So thank you very much. Oh, shame. Thanks, Todd.
So, but just to remind everyone that if you have any questions, please use slide over to ask those questions. And also remember, I'll remind you again, but there is a feedback option on slide over, which you can also utilise to give you feedback on this event. So, Next presentation is from Rob Strugina on the deep water operations. So over to you, Bobby.
Good morning, everybody. I'm Rob Strugina. I'm listed as STEM ambassador. So I'm technically a retired cable engineer, and I go into schools, and my main presence here is so I can. What's changed massively in the industry is there are so many new players, and I find meeting you and finding where you come from and how you got here helps me tremendously when I go into schools. So the information I provide to kids is up to date. But I am a long-term serving engineer, and I'm going to take a huge risk now. I'm going to go much deeper into the detail, a little bit of maths. And if you fall asleep, you're forgiven. If you're shallow water people, you can go to sleep anyway. Deep water. Now, I'm an engineer, and all engineers, we stand on the shoulders of our predecessors. And today, I'm standing on very heavily on the shoulders of Zajac, Roden, and Richardson. You probably don't know, never heard of them. Zajac is particularly famous. He was the man who managed to work out the maths of cable laying. It was in an ATT publication, probably 1950, I can't remember. I've unfortunately given my only copy to the museum. But if you want to know what Richardson and Roden developed his ideas, and this is the Bible. So before computers and all that stuff, this is how we did it. Everybody who had to do a cable lay had to understand that. Now, as my life's gone on, the computers have come in. I can remember the very first time I used a continuing program on a ship, and it was going awfully wrong. We lost the plough in 600 meters, and we had to do a turn of the ship. And I was incredibly tired. I'd been up 36 hours, and I remember I've got to do this. And it struck me: computers don't get tired. So as long as I've got the data right, we got the answer. It was an amazing moment for me. So, but what I've also noticed now is in my personal view, we've become over-reliant, and that the fundamental understanding of how cable laying occurs is being lost. So today, with huge risk, I'm going to try and pass on to you. I'm going to try and make cable experts in 20 minutes. Impossible. Right. Which is the best one? Right. Two types of cable. I'm going to talk about the shallow water cable. You've had a lot about this, but I will pull mine out. This is the one that's taken the stores, but get it out. And you can see that a lightweight cable is very small. This is previous generation. They're now only 17 millimeters, or even less. This is about 20. And you can see a feature of a lightweight cable is that the center is a solid, not solid, it's a wire core. It's very tightly wound, and it creates a pressure resisting hole. So inside, despite it being deep down, it's atmospheric pressure, and that's where the fibers fit. You can see the fibers there, and I keep them covered. They're so pure that if you get one in your eye, they can't see it extracted. So we treat them as sharps on board the ship, but that's all you've got, and that's carrying terabytes of data. It's almost impossible to believe. But also, you can see a little bit of copper there. That's powered so that we can boost the signal along with these amplifiers, and that you can have up to 10,000 volts. So when you're dealing with one of these, you've got 10,000 volts on it, and the optical risk, the laser is strong enough to damage your eye. So altogether, quite a high engineering content and a little bit tricky. And if you've ever been on a ship during a repair and you've got the end and somebody turns the power on, I tell you what, it's terrifying. I've been there. Obviously, it's fine. But the only difference, there's another type of cable. It's exactly the same, except it's got a jacket on it. And I'm meant to move over, just move on. And the difference is these are used in areas where the seabed is not so benign. Normally, the seabed, large areas, we call it Atlantic mousse. You pick it up, it's like angel delight in texture. Imagine that. But it's not always like that. And this particular cable has been recovered from in there. This is off Newfoundland. There's some underwater volcanoes. You can't lay over them. You've got to go through them, but it is a bit rocky down there, rough that way. And they put an extra jacket on it, give it a bit of extra strength. And you also see a bit of metal there. And I think I've got sharp lights. I know we all had a laugh about it. I saw one of the first shark bite cables in the 70s, right? It's a very small area, and they put that on to stop it. It's from memory, it's near the Canaries. It didn't last long. Once they started doing that, it's a very small area where this occurs, but it did actually occur. And I remember seeing the shark bite. I was amazed how small the teeth were. Anyway, enough of that. No, deep water laying. Zajac, the major thing he realised in his calculations was, as the cable's deployed off the back of the ship, it's quite small and it sinks. It's sort of supported by the sea as it sinks. And what you want to do is you want to arrive that the cable on the seabed is at zero tension, so it can conform to the seabed. Now, the maths of it, if you go through the maths, it's almost unbelievable, but it's true. I've seen it so many times. I believe him that the catenary is actually a straight line, right? It's unbelievable, and the angle of that it leaves the ship is remarkably small. The faster you go, the shallower the angle is. But as long if it's below, as long as it's below, that's right, we're at 30 degrees. The assumption's correct. You see, once it starts to become more vertical, it's slightly different. But when it's in that lay condition, that is the solution. And the touchdown point, some of these angles are quite small. They can be as low as 6 degrees. And if you think about that, that means the touchdown point is, if you're in 8,000 meters of water, the touchdown point can be up to 25, 30 kilometers behind you. That takes a bit of thinking about. So what you've got to do on the ship, who's driving the ship, they have to think what's happening 30 kilometers behind them, right? So that takes a bit of thinking about, doesn't it? You see what I mean? When it's all computer controlled, people forget it's back there. Now, not all seabeds are flat. They can slope more than the cable lay angle. And if they do so, you can see there, it's a crude diagram, you get a suspension. So what you've got to do is make sure that your lay speed is correct for the seabed angle you're encountering. But it's not the seabed under you, it's the seabed behind you. And what you've got to do as well, which is even more horrible, is you're belting along at, say, 8 knots or something like that, and you're going to have to slow down. But that cable takes hours and hours to sink. So you've got to anticipate all that, start to slow down, so the transition, as we call it, lands in the right place. You can see why they use computers, right? In the old days, it tells you how to work out the transit times. But unfortunately, the seabed isn't flat. Mostly it is, and this is a condensed view. This is the first fibre optic cable across the Atlantic. My lot only did the UK end, but we did the first one and buried most of it for the first part out of Widemouth. But where it drops down, you surface laid, we use cable like that. Now, this is where I want to go back to this map. In here, he discovered that the lay speed, you need to adjust the lay speed to the angles of the contours of those, the Atlantic ridge, right? And this is he calculated, amazing amount of work to do this. He calculated what happens if you go fast. So if you go more than a knot over the mid-Atlantic ridge, you can see on the axis on the left-hand side, it's the percentage of suspended cable. So there's nothing to stop you going at 6 knots, but if you go at 6 knots with a lightweight cable across the mid-Atlantic ridge, up to 30% of it will be in suspension. Some of those suspensions will be 5 kilometers long. So what happens today? Who is making that decision? Who is deciding what speed to go? You've heard Richard go on about the commercial pressures. Everybody wants everything free on the telephone, and yet the cost of the ship's expensive. You keep the cost down by going faster. By going faster, you leave it. Go into suspension. Who is making that decision? Another example is the Japanese trench. Now, I'm only talking about. Unfortunately, I can bring it and talk about that experience. I know there's other areas worse than this, but I've worked. These I know quite well. The Japanese trench is another one. Now, this one you can see goes down to 9,200 meters, and what happened here? What also you can see is the trench. I can remember going there. subduction zone. We're all taught it, school, subduction zones, it's going that way. Look at the bottom, it's flat. The actual bottom of the trench is flat. How can that be? Anyway, that's another side issue, really. I thought we were at the limits of our instrumentation. So we did it 3 times. Then I phoned Andy and said, Andy, you could check this. He went on Google Earth and did a magnetometry, whatever it is, gravity link measurement. He told me it was in fact flat, right? So reassure us. But you can see the problem. Now, if you're going down that slope, you can see it goes down, but around that point there, SP, whatever it is, RT16, you can see it reverses. Wow, that is really, really hard to get right. Worse, there's a corrosional current. Now, if anybody tells you they know you can model the corrosion current, they're lying. It's impossible. It changes from day to day. When you're out there, we sit there, that ship wander around, and let's hope it gives us a clue. But we have no idea. I certainly never have what's happening underneath. So when you're doing those things, when you think about that layback, it's 30 kilometers behind you, you don't even know what you're laying it into or what you're laying it through, but you've got to get it right. That's where the experience comes in. And I know no other way. And so when I'm out there, do I rely heavily on the Japanese ship? Because they are phenomenally experienced. Now, what happens? If you haven't got it perfect, you get a suspension. And this is what happens. Down there, the seabed, I've told you, it's all like the moose and all the rest of it. It isn't. In these areas, the actual, no, this operation was long. I won't tell you how long, many, many months. And but I asked the ship when they brought the cable in, would they work with me, and we will examine every meter as it came in, every meter, hundreds of kilometers around. And this is what we were finding. Every now and again, we find this. And can you see it? And if you measure the gap there, what it's laid on is very, like in Cornwall, you get that shale, very sharp shale. When you walk on cutting these, it's that sort of stuff. It's down there. It's not covered in sediment because it's too steep, and the cable is there. And because of that corrosion current, it's obviously a suspension. It's doing that, and it just chops its way slowly but surely through the cable. And there's another one getting bigger. And there's the fault. You saw that fault on Andy's yesterday. Now, that cable was kept working by adjusting the voltage. We could make that a virtual earth, so you could keep the system switched on by adjusting the voltage. Say, just for example, it's 10,000 volts overall. You go 7,000 at this end, 3,000 at that end. That puts 0 volts at that end. You can then keep the current flowing because it's not leaking to earth. It's a fantastic trick. Right, so we could keep this going while we mobilised the repair. It took us a year to plan this down, so deep. But you can see when we went to pick it up, 85% of the strength of the cable was lost. As we were 12 nautical miles away from it, long way from it, it went because we just touched it. The tension reached it, and it had no strength. The fibres were still working. I find that still to this day. I find that. So there it is. Right, so now, what I say to you is computer programs are used to plan and monitor cable lays. If you are the project manager, which I've often been, find out who's making the judgment call on the lay speed. There's no technical impediment for them to go faster. And so somebody is making a judgment on the possible suspensions. Find out who it is and have a chat with them. Make sure that you'll know straight away. They say, oh yeah, we're doing it according to Richardson. Or ask them to show you the workings. If you don't do it, you have abdicated your responsibilities to somebody else who's under commercial pressure to do it as fast as possible. In my book, that's your fault, not the operator. Check the operational team has been part of the process. I've been involved in so many cases, and it's sad. I talk to the team who've done it. They've read all the instruments correctly. They have done absolutely nothing wrong. And yet they've got a load of loops on the bottom, or they get the suspensions. And that's because computer-driven, the basic understanding's missing, and the contractor, the cable owners, put too much commercial pressure on. Right. Now, that's the laying bit. I hope you're all experts now. Don't go too fast, you'll ruin it. All right. Second bit now, cable water recovery. This is a completely different ball game. During recovery, the cable has to, instead of supporting it, you can imagine now the cable's coming through like a cheese cutter, but you're pulling it up. So this, in this case, the hydrodynamic forces are not helping you; they are working 100% against you. And now, what is very strange is that small changes in recovery angle produces large changes in tension. Now, whoops. Yeah, right. Now, again, I'm borrowing from this man, Zajac and Rogan Richardson. They did all the work on it. And what you'll see, it's quite a complicated slide, this, and this is, I'm taking my biggest risk now. Please bear with me. What I've done here, I've taken a typical fiber optic cable. It's got a breaking strain of 70 kilonewtons. Now, just for, you can see that 70 kilonewtons appears on this chart. What that's telling you is when we're offshore, we have none of the safety factors that go with, say, lifting equipment from docks. We are working to the breaking strain of the cable. We're allowed to work up with no impact on the cable to about 70% roughly of its breaking strain. But just remember what you're doing. You're sending people out there in rough weather. There is nothing, they have no safety factors. If they get it wrong, the cable breaks and they get decapitated. So when you're putting pressure on the ship, get faster, go faster, that's what you're doing as cable owners. Now, I've modeled one, that's one of these cables here, breaks at 70 kilonewtons, and I've worked out the forces required to recover it in a moderate sea state. And you can see we're allowed to work to 50 kilonewtons, we're working at 50 kilonewtons. But look, look at what it's plotting, it's the angle of recovery. So at 90 degrees, this is its bottom line. And you can see we only have to get up to 0.6 of a knot. Is that right? Yes, it's 0.6 of a knot, and we're right on the breaking strain. So what does that tell you? If the man is at the front was keeping an eye on the angle and the lead, and they haven't got the recovery speed matched exactly to the cable incoming speed, you can see as it goes up very quickly. If the angle's not 75, the difference between 90 degrees and 75 is very small. But look what it does to the load. So when you're sending these guys out in deep water, you're right on the edge. Right on the edge. A small change of angle. The human being, by the way, is absolutely useless at judging angles. So this is what we're doing. This is what we require of them to do. And you can see it's ever so easy. It's really easy to break it. Next. So the impact on the timescales. This is just a typical 6,000 meter. Fortunately, not many. Using a typical recovery speed, if you're lucky, you can get up to 0.2 of a knot. 0.2, nothing. Just to lift the grapnel with the cable, it will take over 16 hours. That's just lifting. That's not finding it. That's not hooking it. It's nothing like that. Just to lift it. And if you put if you add bad weather, you put a repeater in suspension, or you have those subsea currents, it just gets worse. It's very common when you're doing the deep stuff in those difficult places. That's the Japanese Trench, and there are a few others. You're down to 0.1 of a knot. You're down in 8,000 meters. It takes days. Get it wrong, takes days. And all the time, where is it? Where is it? We want it back. We want 3 phone calls. Please be patient with the ship. That's all. That's my single request. Please be patient with the ship. Oops. What they're trying to do is that's a cable coming up to 7,000 something odd meters. We've hooked it with what's called a holding grapnel. You can see, to make sure it doesn't slip off, we grabbed it. We've had to damage the cable to do it. We've got 2 high tension legs on the either side going to the full water depth. We have to get there and get that cable off without killing people. We already know the cable's damaged because we've damaged it ourselves there to get hold of it. Again, do not put pressure on. That's what they've got to do. That's what they're doing for you. Now, so that's my gripe over. That's my long line. That's my deep water repair operations. Please be patient when they're out there and don't force them to go fast. You will get a bad product. Right. Last thing we're going to deal with, long line fishing. Now, I have a huge regard for fishermen. I've worked closely with them and they've saved my bacon loads of times, mainly by keeping guard of my mess ups where we fix it. Now, when you do any job, you normally get a sort of a fishing risk assessment, so you know what you're up against. I'm dealing with deep water, so the main one out there is long line fishing. And you can see on this chart, there's some places where they noted them. But I'll be honest with you. I know there's a requirement that all fishing vessels have AIS on, and I think it's Robert will tell me it's over how many meters? 15 meters. They're supposed to, but they have to. They're meant. They have to have it. They have to broadcast it, but there's no requirement on them actually to really, make sure they're there. And fishermen are very private about where they fish, and I'm some of the I've come across it everywhere, and often where it's not meant to be. So, what am I talking about? Well, if you're lucky, this is in Japanese waters, so they're very good out there, very very cooperative as well, very powerful fishermen. You can see this is all you see. You're going along with it, and then somebody has to spot. And what this is they're long lines, and what we're dealing with. This is an older version. This is a Spanish one, and it's basically long lines, and they can be up to. To be honest, I've never encountered the vessel. Only once encountered the vessel. They don't want to talk to us. They don't want to know we're there. We're a nuisance to them and all that stuff. And what they do, they have a radio beacon on the end of the line. It could be 50 kilometers long. Right? It's a 50. In my view, it's 15. It's a 15 kilometer hazard, which is almost invisible. And on the end of it, hanging down so many meters below, there are these. And I'll leave them out. You can all have a look at them. They're protected. They will, health, safety, it's sharp. Right? And that's what's going along. And it's 50 kilometers. And you don't know. And if you're lucky, like in this case, we saw it. We whoa, tried to contact ship, the fishing vessel, and in Japanese waters they usually respond actually, and we come to some agreement on what we're going to do. But it's a nuisance. It stops you, right? No, but if you're unlucky and you can't talk to them, you've got to get rid of it. It's in the way. Look at it. Those hooks are the perfect diameter for catching a cable. I've unfortunately made it safe, but you can see that fits on there gently, and I'll come to it in a minute. That's what it does to your wonderful product that you paid a fortune for. And that's what it looks like. So here we're clearing it out the way, and you can see it stretching distance. If you're lucky, or unlucky, I'm not sure which, when you're doing the recovery, and here we're doing the recovery, you can see we've noticed it a little bit late actually. The chap on the foredeck has seen it round the cable. If you're slightly more lucky, these curtains will have caught a byproduct. They're not after this, they're after tuna. They will have a turtle on. And that turtle, the hook is through its beak, and it has saved our cable. We're in the middle of the Atlantic. We only have one rib, but we don't tell the office, obviously. We stop the ship, we stop the operation, we launch a rib, and we rescue the turtle. I've got a beautiful video of it. I would have loved to show it to you, but unfortunately time doesn't permit it. But you can see there's our rib. We've gone out there. We've had to bring it back because we land our dentistry tools over the side, so we can release him from the hook. That is the hook. And then we took him a quarter mile off because we didn't want to go to the tops. So for those environmentalists here, you'll be surprised how thoughtful us cable ship people are given the chance. Now, if you're less lucky, it gets worse, and it's coming in. This is a joint post coming up, something like that, and it's wrapped around there. But now this is serious, right? It's wrapped around there. How the hell's that happening? This isn't a live operation. There's no fishermen. This is becoming really serious. This means this cable, this hook, has been on that cable since it went in. We're picking it up. There's no fisherman. There's no evidence of it. There's no dog. This stuff is coming around, wrapped around it. Now, this is a project where we're recycling this. It's had its economic life. It's an island somewhere down in the Caribbean that wants to break the monopoly of cable wireless and all that stuff. And so I've got together with a few people, or they've got together with me, put it that way. And we were going out there, we're picking up this out-of-use cable, and we're re-engineering it on the ship, cutting it out, rearranging the cable segments, putting repeaters in the right place, all that stuff, so that we can reuse it. Recycling, 100% recycling. This is completely frustrating us. This is wrecking the very thing we're going to use. If you go a little bit further, you can see, and I've got it here. This, the two cables, this is actually from that operation. You can see this is meant to be reused, going connecting that island. Well, it isn't. I've got it here. Right? This is bad news. Now, so when you're talking about that, I saw it coming up yesterday. There's a big emphasis on reuse, and all that stuff. Remember this before you stop. Well, please do it, but remember this. You, oh, you can pass around. Yeah, sure. Now, so what I want to say with that case, I was running it. What do you do? Come on, imagine what you're going to do. What the hell do you do? You have no idea. How long does it stretch? Like, is it 50 kilometers I have to worry about? What the hell do I do? So what I actually did, and it's very useful when you do this, make sure you read the logs of the ship that did it. So I got out the logs, worked out where it was, what day it was on when it laid it in that area. And I went through in great detail. I noticed that when the night shift came on, they forgot that, the day shift, as they were changing it over, they normally deploy a long line cutter in front of the vessel. So as you're going along, if you don't see it, and at night you probably won't, it's in everybody's interest to just cut it. And then it falls outside the ship, you lay through it, you don't trap it, you don't take all that gear down below, wrap around the cable, and the fisherman, he's obviously going to be annoyed, but he can, through his radio beacon, he'll know straight away that it's done. He can bring his line in, go round to the other end. The only thing he's got is a brake, which he can fix. So what you want to do is and what happened on this job, I went through all the log records and I realised that night shift had forgotten to put this out. But what that did, it told me the length of cable and where it was, I could dimension the risk area. So I say, right, what we've got to do is we've got to let this go, put it back on, we can leave it there. I'll go so many kilometers beyond it, start again. And sure enough, when we picked it up, gone. So we had to re-engineer the whole thing again to allow for this missing bit. But you can see that tiny bit of planning and a bit of operational skill, making sure. And these, by the way, are made with that. Okay. And I've said before that I'm an engineer. I stand on the shoulders of other engineers. But to be honest, on all these operations, and I've worked a lot in Japan, and I'm often sent there because I get on really well with Japanese. And this is my award-winning team, if you like, or my record-breaking team. We owed at least 2 world records. But it's not us. It's not me. It's definitely them. They are so good. But they do let me. Some operations are so tricky. I'm hugely privileged that Mr. Sato on the left, I know he plays computer games, and he's really the world's best operator of two cable machines at the same time. So remember, though, but if you're ashore, you're directing our operations, you're telling us what to do. Remember, be part of the team, be part of us, and you'll get a better job. So I hope for that, and it's very, very exciting and rewarding to be part of a successful team. So I hope that's enough.
Thanks, Rob.
Oh yes, sorry. Thank you. Yeah. No, sorry, my fault. This is us doing a recovery operation, summertime, North Atlantic. And we're going quite slowly because that's the bit of that cable we're picking up, and just a routine day. That's a good example, right, of what I call. If you go into this, if you do ship design and all that, you have to understand that every sea is different, every ocean is different. All the data is here. It's in this library, actually. You can find the waves. It's called the wave spectral density. And if you study that, and you should study it, you'll find that on average, there's always probabilities and all that, but every 36 hours out there, you'll get one wave twice the height of the average of the third highest. If you think about that for a minute, that means every now and again you get a rogue wave. It's a maths thing, sorry, but it does mean every now and then you get one of those. It completely catches you it can catch you off like it did this time. See what I mean? Just another risk. Sorry.
Okay.
Thank you, John.
Any questions?
How do you account for those waves in terms of the tension?
How do you keep the tension steady given those waves?
You can't. That's it. The answer to that. No. I'm very fortunate. I've been in this game a long time. Most of you have shared me how you got into the game. I got here by accident completely, but I've always had a passion for measuring forces. I started by measuring. We had a tower shaking in BT and all that stuff. So I was asked to solve that. And the cure to it, or the solution to it, was understanding the energy density at different frequencies. Now, you're all telecoms people, you all understand frequency domain, but it's not normally used that much in the mechanical domain. So I adopted a telecom technique into mechanics. And so when the first time I got on a ship, I'm sure the maths is wrong here. So I instrumented the ship. This is in the 70s. I'm mad, with tape recorders and that. And I measured the ship, movements, accelerations, and all that, and helped with people like here to develop the spectra that we use for fiber optic testing beforehand. Right. So I've obviously got it wrong here, but what I do, and I use the library downstairs, is if I'm doing a deep water operation, and that operation I was talking about in the Japanese trench, we did in the middle of the winter. Nobody wanted to go, but you can see I knew that cable was corroding. I knew it wouldn't last another 6 months. So I asked them to go 1st of January, or actually day after. And they accepted that my calculations on the maximum strain would not be exceeded if we did it right. I got the data from downstairs and it worked. I was really, thank you downstairs. Right. And it worked. But you can't control it, you just have to not exceed it.
Thank you. I did put this question on the slide, but it's I'm Chris Page from Historic England, but don't worry, it's not an archaeology question. But with what you've just been describing about the repair work and the strain being placed either on the electricity or telecom cables, what is the likelihood of then increasing the risk of subsequent failures of that cable? And therefore, is there a law of diminishing returns on how much you can repair a cable?
How much you repair a cable? Right. Oh, that's a complicated question. All cables, certainly telecom cables. What happens is when you do a repair, the section gets longer. Now in deep water, the length is huge. You can imagine the minimum. If it's 8,000 meters, the minimum you're going to put in is 16 kilometers. Now a section length typically is 50 kilometers, but if you add 16 kilometers into a 50-kilometer section, it doesn't like it. You've got to do something about it, and often you have to put another regenerator. So that you can see, and then when you put another regenerator in, you upset the balance of all the others, and sometimes you have to equalize it. So life becomes very complicated, and there is action. There comes a moment where you say, "I can't do this," and let's say, as Richard says, there comes an economic point where you say, let's just start again. It's not worth it. It's so expensive to repair. And often, sometimes just say, I've got so many repairs in that bit, I've got to replace that bit. And that bit may be 100 kilometers. So there are limits, there are limits because it doesn't work. Every joint is a loss. The signal gets degraded and it may not be recoverable at the other end. Does that help? Does that answer your question? Yeah. Okay.
Thanks, Will.
Okay.
Okay. Doesn't matter, shall we? So we've finished the section on repairing subsea cables, and now we'll go on to the section of protecting cables from damage. And the presentation will pop from Andy Felgate on global repair commencement time analysis. So, is Andy here? Yeah. Oh.
So I thought it was coffee break time.
No such luck. That lucky, no. There's the
Okay, thank you.
Thanks a lot. Thanks, Rob, for an excellent presentation. I did just want to say, in follow up to that, I was involved in one of these repairs with Rob a long time ago, and when the repair fault first occurred, I spoke to my boss and I said, "This is going to be a really big problem to sort out." And he says, "Well, there's only 5 people in the world who are knowledgeable enough about cable to go and sort this out, and one of them is Rob, who lives down in Lymington. So hop on the train, go to Rob's house, and he'll help you." So I did, and he very kindly gave me a copy of this book, and he basically said, "Take this home with you, read it, understand it, come back in a week, I'll test you, and if you get enough questions right, then we can work on this repair together." And so we did, and it was fantastic. And then at least a decade later, I was involved in another incident, different one. This was shallow water, but it was the same principles applied. It was a shallow water problem, but it was about suspended cable. And thanks to Rob, I was able to deal with it on my own that time and get it sorted out. But I think it does go to show that it's not really a scalable solution for the industry when you've only got 5 people globally who really know this stuff and they pass it on in this way. As time goes on, we need to do a bit better. So, but thanks, Rob, much appreciated. So I'm going to talk to you about the global repair data set that ICPC curate and update annually. Wanted to say to begin with, though, just a few things about networking. So, the global networks are huge these days. Just the Meta network itself connects over 3 billion monthly active users, live in a world of about 8 billion people. So, it's a huge portion of the population connected via these networks. And we talk about network resilience, but what does it really mean? It's about keeping these subsea fibre cables so that they've got low time between repairs. We call that the mean time between failures. That has to be kept to a minimum. But we also need to have the mean time to repair, the repair durations when they do fail, kept as short as possible. So when you put those things together, you end up with an availability statistic, and that statistic can be worked out either on an individual cable or across a network. So take an example where you've got your cable, you get one repair annually on average. That repair takes about 36 days to complete. That gives you an availability on that one cable of 90%. It's down for 10% of the time, is up for 90%. We call that 90% availability. We add another cable to that network to create a diverse backup path. And as long as we've got enough reserve capacity to do the failover, we get an order of magnitude increase in availability. So that then gives us 99%. And as Paul mentioned earlier, networks these days are striving for 5 nines availability. That's 99.999%. And to achieve that on long distance subsea networks, you need to keep both your mean time between faults as long as possible, so you get few faults, and you need to have these repair times kept as short as possible. And I think it's a great it's a great thing really that the public rely on the global internet, and they don't really understand this stuff. They don't ask any questions. They assume it's all in the cloud, and it's been a secret for a long, long time, thanks to the way that these systems have performed. But as the industry comes under more scrutiny, we do need data. We need to be able to show that we're monitoring these things and looking at trends, and that's where the work of the ICPC comes in. So I'll start the presentation. So as Paul explained, we have these different maintenance agreements. So you can see we've got the zone agreements on the top right that cover most of the world. And then you've got an overlapping private agreements that also cover the majority of the world, and provide some competition and provide an alternative depending on commercially what you want to put your cable into. You can see that off of the west coast of the US, you've got no choice. It's the North America zone or nothing. And similarly in the Persian Gulf, it's the E-Marine agreement or nothing. So, there's some places where you've got no choice, but most parts of the world you can put your cable into either the zone agreement, which is more like a syndicate consortium type thing, or the private agreement where you just have a direct relationship with the service provider. So the ICPC has been tracking cable faults and cable repair times now for since about 2011, 2012. This initiative was initiated with my old colleague Nigel Irvine when I was at Verizon, and we had access to the data from the zones because they would provide us with commencement and completion notices, and we started to sort of collate this data, see if it could be shared. But people are a bit sensitive about repair data. It is commercially sensitive to cable owners. They don't make available to the public every time they've had a cable fault where it is, what's caused it. They feel like they don't need to really because the network is so resilient that one fault individually is not always relevant to how a network's performing. So we wanted to try and collate this data in an anonymised form, just to provide some more general information, which we were able to do with support from all of these data providers. So we've got a massive number of faults now, or repairs, 2,857. Annually, there was 206 in the last time I did this analysis last year on the 2023 data, covering 136 different jurisdictions. The average notified to departure time from when you call out and say, I've got repair, I want you to go, to the ship actually going was 21 days. Then it took an average of 7.5 days to get to the repair ground on top of that. The longest repair delay that we were reported to us was 947 days, incredibly long time. And the percent of these repairs that were service affecting, so people mentioned earlier, you can either have a shunt fault, which is not service affecting because the power feeds can balance and keep the traffic up, versus a complete break in the fibres and an outage, that's 51%. So about half of cases, the traffic can be kept up until the ship arrives on site. So looking at the distribution of repairs, firstly, look at the pie chart. This shows that the orange, which is EEZ, that's where the majority of cable faults happen. So I work for an American company, I say EEZ. So 54% happen there, which is not surprising. That's the vast majority of the continental shelf area. And that's where all the fishing and anchoring generally is happening, not too surprising. 44% in the territorial sea, the areas closest to land. And then only a tiny fraction, 2%, happen within the high seas, which is beyond 200 nautical miles from shore. Looking at the number of repairs per year, so the number of repairs here is the blue bars on the bar chart, and you can see it varies. It can be around 150. Some years it's topping 200, but it stayed fairly flat. So the number of repairs per year, going back to 2010, has averaged around the 200 per year mark, or just over, fairly consistently. But the number of in-service cable kilometres, which is the green bars, that's risen. What this says to me is we're actually doing better as an industry now because the fault rate per kilometre is diminishing over time. So we're doing something right. Good news. Then last thing I just wanted to notice the number of repairs in the high seas by ocean. So you can see the Atlantic here is blue, Pacific is green, Indian Ocean is red. Very, very few repairs in the Indian Ocean and the Pacific compared to the Atlantic, which is interesting for a few reasons. I think it shows that, those other oceans, we tend to, have a lot more of this Angel Delight type seabed Rob was mentioning, lots of flat abyssal plain. The Atlantic has a mid-Atlantic ridge, so more chance for abrasion. It's got Gulf Stream current and various other deep water chances for the cable to become damaged. So this map shows repair frequency. Colours mean time between or days between repairs. So the dark colours, the sort of burgundy and the pinks, their repairs happen in those waters every 12 to 30 days. So we're getting really frequent repairs, as you can see, around the British Isles, the South China Sea, and other parts of Southeast Asia. Other repair hotspots in Indonesia, Malaysia, France, Canada, and India. And then there's lots of parts of the world where you can see they're coloured in the sort of green, yellows to greens, which means that well over a year goes by without a single repair. And in the blues, you're looking at many years. Looking at sort of 5-6 years goes past before you get a single fault in those geographies, because tend to have less hazards, more deep water, and in some cases just less cable. Now, that's a number of repairs. What about the repair response time? So the number of repairs, as we saw, it stayed fairly flat over the last decade or so, but the repair response time has more than doubled. You can see that back in 2012, the average repair response time from being notified to starting the repair was just under 20 days. Now we're up at almost 50 days. So this is a big problem. When you think back to what I explained earlier about this availability calculation, number of faults, mean time to repair, it means that our availability across the global network has diminished significantly because of these extended repair response times. So just to put this geographically, here's another map showing with the colour codes where repairs get done fast. That's the blues and the greens, and where they get done very slowly, which is the pinks and the burgundy colours. Now, there's some reasons for this that I'll come on to, but you can see that it tends to again be those Southeast Asian countries that are having the difficulties, along with some areas of South America and the Caribbean. Sorry. Yeah, so this one just adds on the transit time. So this is, the previous one was from notified to the ship leaving port. This is from notified to the cable ship arriving on the repair ground. And you can see I've put the sort of ship symbol to show where the base ports are located. So often it's where you've got a very long transit, like down to the bottom of Argentina, for example, where you've got that extended repair response time there because it's so remote. So regional differences, we see that the number of repairs per year has only risen in the Eastern Hemisphere agreements. It's shot up there. It's remained fairly flat elsewhere. And why is that? I think it's because the number of repairs has gone up so much in Asia, and it's put pressure on the queuing. So there's a lot more waiting time for cable repair ships. But there's also something else going on that I'll come on to in a second. And that's the permitting and the regulatory environment. So it's always been difficult, but it's getting a bit harder. So we're seeing that for particular countries, particularly the ones listed here, the number of days just to get the repair started is really shooting up. And it tends to be down to these reasons I've listed. So vessel importation. In Brazil, you've got to import the ship into Brazilian, through Brazilian customs. You've got to put up a bond to the value of the cable ship before you can start the repair. Same applies in India. In Indonesia, you can't turn up with any cable ship. It's got to be an Indonesian cable ship. So that's a problem. Hong Kong, massive operational permitting time frame. Then there's often security clearances. You can understand that, if you're in the UK and you've got the sovereign based in Portland and it's all British crew, there's no problem. Everyone knows that, this is safe. If you are in a foreign country and you're looking to get in a foreign vessel with foreign crew, you might be somewhat suspicious what they're going to be doing on your cable. So there'll be a process that they want to follow, which is understandable. But if that drags on for weeks or months, it's not good news. So government best practice for repair permitting. I mentioned the case of the UK, but there's other countries here who don't have cable ships that are sovereign cable ships. The Netherlands and Belgium, they don't have their own cable ships located within their territories, but they're still able to get repairs done, in about a week. And why? How can they do that? It's because the government have basically a pre-permitting process where they pre-vetted the vessel and the crew. They're able to offer an authorization very rapidly for that ship to come from either the UK or the French base port and get things going. South Africa, they benefit from having a ship based down in Cape Town and a pre-permitting regime. This explains how, when you look at the reason behind the delays, a lot of them are the reds, which is the permit delays, and the yellows on this bar chart. So I'm waiting for a ship often overlaps with waiting for a permit. So you can't really solve the two in isolation. We've got to sort of try and get these permitting durations down, but also bolster the number of ships in the regions where there's constant queuing. So it's a two-pronged approach towards solving this issue. We're also seeing that there's sometimes more planned repairs. So this is where cable owner will say, actually, I don't want you to go and do my repair tomorrow for whatever reason it might be. It could be that they need to do a lot of planning, in the case Rob described, deep water repair. It could be that they don't like the time of year and it's a shunt fault. They might need more spare cable, or they might simply not have the money to go and do it, which we've seen in some cases. This is also something we're tracking, and there does seem to be an increase in the number of owners opting to delay cable repairs. I don't know if you can see it for those sat at the back, but there's some charts here just on the fault causes, but that isn't really the primary purpose of this presentation. Last thing just to conclude, so what needs to change? So we're seeing this trend. I don't think it's sustainable for the industry. It's not efficient for the internet as a whole to have these very expensive cables in the water that are sort of in some cases sat idle for a long time, waiting for a repair vessel, waiting for a permit to allow permission for the repair vessel to go in and get started. So we need to do better. And I think for agreements in the West, the number of repairs hasn't changed, the number of maintenance vessels hasn't changed, so there's no reason there not to do better. For agreements in the East, it's a bit different. We're seeing a vast increase in number of faults, and that needs addressing with more cable ships on standby to go and serve those repairs. And then lastly, government action. So we're hoping that more governments will adopt the ICPC best practices when it comes to pre-permitting and expediting these repairs. Very excited that the ITU has recently formed a partnership with the ICPC to create this advisory body on government best practices. And I think that will be a great opportunity for governments who, via the ITU, can finally, hopefully, get the message and start to adopt some of these processes which ICPC has been promoting for quite a long time now. So just like to acknowledge that this wouldn't be possible without the support of all of the zone agreement chairmen who facilitate this, private cable providers, and some of the ad hoc repair providers in the Baltic as well for providing their information. So that's it. Thanks very much. We'll welcome any questions. Yeah.
Okay. Next presentation is from Peter James.
That's not mine.
Give me 1 sec. 1 sec. Do it quick. Sorry, Peter. I've given you the wrong slides. There we are.
All right, so I'm going to talk about charting and monitoring. And when I say charting, I'm not talking about Admiralty charts or UK HO charts. I'm talking more about Kisorka and the cable lens charts that they produce. So the question is, to chart or not to chart? That was one of the first questions actually on the agenda at the very first ICPC meeting way back in the 50s, I think it was, when we even called the ICPC. And it's still a valid question today because you have to look at the pros and cons. So what's the best reason for charting your cables and letting people know where all your assets are? Well, the best thing is it lets others know where your cable is. So that's a really good thing if you're trying to avoid damage. But what's the number one reason against charting cables? Because it lets others know where your cables are. And then you ask yourself the next question, well, what's the express reason for it? Well, if the location of the cable is known, it can be avoided by others. But then someone will say to you, well, if the location of the cable is known, then it can be targeted by others. And it's funny because you have the question now of the Russian mania that's currently ongoing, and saying like this, the Russian ship, the Yantar. Never know if you've heard of that, going around charting cables. But the Yantar doesn't have to chart cables because you can just download it from the internet if you want to. So I think that's all a little bit of scaremongering. And then, so that's where those two align. And then the arguments against sort of fall away. Then there's more arguments for, if an uncharted cable is damaged by a third party, then the third party has a defence to say, "Oh, I didn't know the cable was there." So if you don't tell fishermen where your cables are and they trawl over it and damage it, they'll say, "Well, it's your fault for not telling me where it was." And so that will be very difficult if you try to take a civil claim against anybody or ship anchor as well. If you try to take a claim against them, then they'll say, "Well, I didn't know it was there." And also, for efficient use of the seabed, we should map all the subsea assets. You'll have seen over the past couple of days slides from Crown Estate and other organisations where all the cables charted on the around the UK are all on there. All that data is from Kisorka. We give that away freely to the Crown Estate, to the MMO, to all the regulators. So all that information is being given freely by the cable owners. And then Admiralty charts may or may not always be up to date, and fishing vessels may not carry Admiralty charts if they carry charts at all. So it's best to actually go out there and basically put the information into the people's hands rather than go out to get it. So given all that about cable protection and seabed mapping and just general information of where the cables are, but the number one reason why we chart cables and why Kisorka was brought into about is safety. So there's two fishing boats you may not have heard of: the Grey Flamingo and the West Haven. The Grey Flamingo snagged its gear, I think it was 1987, snagged a skier on an out of service cable off the southwest coast and went down, and we lost 2 crew members. West Haven, that caught its trawl doors in a pipeline, and that also went down as well. Commercial fishing is one of the most dangerous occupations in Europe, in the world, and 20 to 25 fishermen are killed each year, which is crazy when you think about it, because it doesn't always make the news. So the MAIB, in one of their reports, said that it was far too difficult for fishermen to get the information of where cables were. They had to go and apply for the information from the MAFF, as it was then, and they said really people should, cable owners and pipeline and asset owners should really be making the information of where cables are freely available to fishermen. So based on that, it came up with the KISCA, which was the Kingfisher Information Services Cable Awareness Program. So back down there, so you can see this is the forerunner to ESCA, the UK CPC, and they set up this program with Sea Fish Authority, and they used to produce these charts, and we used to send them out to fishermen, and we used to get floppy disks and give them to fishermen so they can put the charts onto their plotters. And if they didn't have floppy disks, we used to give them all the basically all the RPLs, all the cables. And so that worked quite well for a number of years. And then when offshore wind started going, we decided to revolutionize the whole program, and we set up an interactive website called KISSORCA, so kissorca.org. So I recommend that if you've not ever visited, go and visit it. It's got an interactive map. It's got all the cables, interconnectors, wind farms, and we set that up in 2012, and that still runs now. And we don't give out floppy disks anymore. It's USBs now, and we go around and we visit ports, we visit the fishermen, they hand out the charts, they go to trade shows, go to conferences, and also we supply the information, as I said, to all the government agencies and the Crown Estate. And then the next evolution of this is the Kingfisher Bulletin app. So I recommend, if you haven't got this loaded onto your smartphone, go and download it. It's free. And if you're a cable operator or owner, you can update the status of your assets in real time. So if you know that you've got a bit of exposed cable, or if you know that you're doing a survey or you're doing a repair or anything like that, you can go straight onto the app and update it in real time. And then all the other fishermen and other marine users throughout there can put on there their zones of interest, and it'll do a push notification, tell them that there's something going on in the area that they're looking at. So that's a really, really useful tool. So that's the charting side of things. So when they go to talking about monitoring, I'm talking about monitoring the condition of the cable, not AIS monitoring or DAS monitoring like that. I mean about the burial of the cable. And these brings up then a lot of questions which I'll go through. Generally, once installed for telecoms anyway, once installed for telecoms cables installed and buried, we tend not to go back and take condition surveys of the cable. As long as we know it's being buried on installation, then telecoms cables just operators tend to leave it. Offshore wind and interconnected cables, they're more likely to undertake regular surveys. Some cases it might be a license condition. On the KISCA charts, on the KISSORCA charts, we don't chart where the cables are exposed because, or we don't, and this is this is like it's open for debate. This is not a closed issue. And some people say we should chart exposures. Some people say we shouldn't. Personally, I don't think we should chart exposures on Kisorka charts because that would imply that we know that all the other parts of the cable are buried, and we don't. So what we can do, because what can happen is once a cable is buried, cables can become exposed. As we said before on several presentations, the seabed is not a static environment; it's mobile. So you can bury a cable, a storm can come through, take away all the sediment, and you've got an exposure. And then a few days later, another storm comes through, and the cable's buried again. So we don't chart exposures on Kisorka charts for fishermen because that would imply that we know that all the rest of the cable is buried, and we don't. So and also ESCA, and we also advise that never assume that a cable is buried. So I would never think it's safe to fish over a cable. And also on burial surveys, a burial survey is only accurate on the day that you do it. So you can go and do a survey, and the cable may be buried, and then you come back a week later and survey again, it might be exposed. So that situation, if you know the cable is unburied, so if you've done a repair and you can't bury the cable and you've got a known exposure, then obviously that should be highlighted because that is a seabed hazard. And if you know you've got an exposed cable and you don't tell a fishing vessel, and a fishing vessel snags on the cable and has an incident, you could be liable for that if you know it's there. So the Kingfisher Bulletin, as I've just explained, is the appropriate tool to know of any known hazards. So the Kisorka charts stay as they are, showing where the cables are. But if you know there's any exposures on that cable, then you do it via the Kingfisher Bulletin, and that should come here. And that was it, basically. So,
Okay, thanks,
yeah.
mate.
Okay, so break coffee now. Be outside and come back. Back at 30:30. Come back at 11:30.
I'll put this on the slide. So I'm not going to do my cable presentation. I'll just scrap it. Mike's going to do some of those bits in his. So after the break, we'll do me, Alistair, we'll do index me, and then I'll do cable protection. Then we'll do Mike's side. Because I did have two presentations, but I'll just do one.
There we go.
Mike, it's froze again.
You just got to click the mouse on it, I think.
I do.
Yeah, there we go.
Okay, thank you.
Shall I stick that with you?
Yeah, I'll try. Okay. Next presentation is from Alistair Godfrey of Indexmate on sensing cables and future technology. So, Alistair, there you are.
Thank you very much. Hello, everybody. So, Alistair Godfrey from Indexmate Limited. So, my background for the last 15 years or so has been with fibre optic sensing, developing that and getting it to use in different applications. And we've been looking specifically at the applications on subsea power cables. So, I'll talk through a little bit about that. I think there's not many time for questions, so if you want to nod me afterwards and ask questions, then that would probably be the best time. So, a little bit of background. I think this is, by the way, one of the most exciting technologies there is around there. In all power cables pretty much that are certainly that are put down now, most of which are existing, and obviously all telecoms cables, you have some fibre optics in that cable. So I've put a little circle around it. They're very tiny, thin little bits of glass, around about 125 microns in diameter, each piece of glass. And it's usually there for carrying communications and information. But actually there's another use for it, and that is to see what's going on with your cable, to look at it in different aspects. And I'm going to talk a little bit about the different ways that that can be used and how you might find that useful for different applications in the cable industry. So the sensing that does this, I've got to be clear on this, the apparatus that extracts that information is off the shelf, TRL9, go and buy it and plug it into one end of the fibre and start extracting information from the fibre. This is not a research bit of kit. And you can get all sorts of information from that. I'll talk through that a little bit. So the principles, how does this work? So I'm kind of trying to think of a way to explain this. So it's basically done by the time of for a reflection to come back to the start of the fibre. So if you think about how a bat finds out how far away the juicy moth is, it lets out a squeak and it listens for the time at which that reflection, that squeak, the echo, comes back. So that's time domain reflectometry. So in the world of fibre optic sensing, you do the same thing but with light, a bit like radar as well. Although in the case of fibre, it's constrained to a kind of one-dimensional line along the route of the fibre. So what you do is you put a short pulse of laser light to one end of the fibre, and it travels along at the speed of light, which is quite fast. And at the same time, some of it gets reflected back towards the star, which you pick up. And the time of arrival of that reflection tells you whereabouts in the fibre you're looking at any moment in time. And the light itself contains the information that you can extract from the fibre. It all sounds a little bit dry, but it is really exciting. I'll kind of show you that a bit. So that doesn't actually cover all of the technologies. There's one extra one I'll cover at the end. So the time which it takes for the light to get to the far end and then the reflection to come all the way back determines how rapidly you can sample that fibre. So for a 100-kilometre fibre, it takes about half a millisecond for light to get to the far end, another half a millisecond for the reflection to come back. Therefore, you can sample it 1,000 times a second. So on a 1-kilometre fibre, you can sample 100,000 times a second. So that gives you an idea of how often you can get a sample of what's going on the cable through the time. So let's have a little bit look at what you can extract from the light that comes back. So one of the most established technologies is distributed temperature sensing. So one aspect of the light that comes back to you can extract temperature information. So this is absolute temperature information. So you can work out that the temperature of the cable is, 31.2 degrees at a position of 25 kilometers down the cable, or whatever distance that is. And you can sample every section of the cable all the time from just one end of the fibre. Now, I think that in itself is pretty incredible. So what I've got here is not a very exciting picture, sorry about that, no dead deer or anything. There's a section of time versus distance along the cable. So on the y-axis, we've just got time. It's a day or so in this case, and distance is probably 30 kilometres or so. And the colour denotes the temperature at which each individual section of that cable is at the moment in time. It's averaged over about 30 minutes or so. And actually what this is showing you is the tide going in and out and changing the temperature of the cable. It's showing you where the cable is buried in HDD, it's at a higher temperature than the rest of the cable, and it's showing you where the cable is on that. So all that is useful information. And if the cable starts to overheat in one region for any particular reason, you can extract that from the information. You can also extract an estimate of the burial depth. So you know that the deeper that the cable is buried, the more it tends to heat up because it's less cooled by the water. So you can get an estimate of that. So I've got some specifications up there. You can do roughly 50 kilometers from one end. You take a temperature sample every 10 or 20 minutes, that sort of stuff. So that's the background. That's quite useful for monitoring to make sure the cable doesn't overheat. And as I say, doing burial depth and some other information, but it's relatively limited. It's still very useful. Oh, real-time thermal rating. I just probably ought to mention that as well. If in wind farms the amount of power that's being generated tends to go up and down quite a lot. So one of the potential uses of this approach is to say, well, actually, we can carry current a little bit too much, as long as we don't do it for too long, as long as we don't let the cable get too hot. So you can maximise the current that's being carried. So that's another use of DTS. So here's another one which is a bit less used. This is distributed strain sensing. So in the same way that temperature is extracted from a DTS unit, the level of strain can be extracted from the light as well. So this has always got to be relative to some starting point. So the starting point is usually just the fibre in its relaxed state. So you can look to see whether it's been strained by a few thousandths of fraction, either above or below that level. And so you can use that to get information. The little plot I've got here, again, is time down the y-axis and then distance along the x-axis. And this is actually some data of a cable being unreeled from the ship. And you can see there's actually strain on the reel, and as it's being unreeled and it goes off the back of the ship, the strain is actually reduced there. Now, it all sounds great, and you might think that's going to be really useful. The problem is, I'm going to go back a couple of slides just to show you this problem. The problem is the cable design. So that glass is quite fragile, and you don't want it to break. And so what you tend to do is to put too much fibre into the cable. It's kind of helically wrapped inside the cable, so that if the cable stretches, the fibre doesn't break. But in order for that to work, you have to decouple the fibre from the cable. So it's kind of filled with a gloopy gel. And so basically what I'm saying is it's not very well strain coupled. So actually measuring absolute strain is only useful when there's been so much strain that the cable's now pulled tight enough that the fibre's pulled tight. So limited use, but something to be aware of nevertheless. Now I get on to the most exciting one. This is one I think where you get the most information. So this is an amazing bit of technology. So here, as I said, you're sampling thousands of times a second. With this approach, it's called distributed acoustic sensing. You don't do any averaging. So with the strain sensing and with the temperature sensing, you're averaging for tens of minutes. With the DAS, you're taking a sample every millisecond or every half a millisecond, or however often that is. And that's a measure of the instantaneous strain in the cable, so the rate at which it's strained. But the point is, it's extremely sensitive to strain. By extremely sensitive, I do mean at any 1 10-meter section of the cable, if it changes in length by an atomic radius, that's around about noise floor, which is utterly ridiculous. You measure in that in a millisecond. So what do you actually pick up? You pick up all sorts of things that are happening on it in the environment around you. So acoustic pressure waves, the change in the water column height from water waves going over the top, that affects the pressure on there. You pick up the vibration of the electricity in the cable itself, so you can look at what's happening to from the electric current being carried on. You obviously also pick up temperature changes, because temperature changes, it strains, you pick up that strain in a different way to DTS. It's extremely sensitive to temperature, and you'll measure it very quickly. So if there's instantaneous little changes, you'll pick that up. And so it's very useful for looking at the state of health of the cable. You can look to see whether, is the cable exposed in this region? Is it vibrating in the moving tide? Is it scraping on rocks? Is there some sort of degradation of the armour? So you can use it to look at what's happening to your cable real time, all the time, from one end of the fibre just sitting in an offshore substation. So that's a really good thing. And I know there was a mention about the dark arts of finding position using different technologies. It's the most clear it can possibly be with that. So this is an image of the same sort of thing, distance versus time. This is what it looks like when a boat goes over the top of the cable. So this is actually about 20 kilometres, and it's about an hour of time. And you can see the boat noise, you can see the sound of the individual waves slapping into the hull, you can see all the blue stuff that comes out the back. That's the wake passing over the cable as it propagates down. So you can see exactly where that boat is. So if you want to go and know where your fault is, you've identified it from the noises it's made on the dash unit. You can send the boat to where you think is the right position and check that it is exactly everywhere it should be. So it's a really good way of being able to monitor your cable. And again, I've got some specs there about spatial resolution and maximum range and all the rest of it. But that's the gist of it. So one more thing to cover, just in the state, just to try and be thorough. This is a slightly different approach. So instead of using a time domain measurement of how far away something is, working from one end of the fibre, if you want to go for a very long bit of fibre, there's not enough light coming back. It's actually quite hard, although there are some ways to get around that. So what this is an approach where you send the light from one end of the fibre and then you look at what's happening at the other. And so in that case, you can pick up if there's any big distortions, if there's anything that's changing, but you can't really get much information about where that is. But if you've got other information that might be able to corroborate with that, then that itself is a useful approach. So I am mentioning that because I think that's something that's going to become increasingly useful, especially looking at long lengths of cable, just so that you know the different approaches that are there. So in my summary, I'm going to say that you need to know about fibre sensing. It's up and coming. There's a lot of data that you've got to deal with, but there's great ways of dealing with that data now. And it's just a good way of being able to monitor what's happening with your cable. So hopefully that was interesting and not too long. Yeah. Well, wildflowers, all good. Thanks, please feel free. Yeah, feel free to nobble me later and ask questions. Unless that's
one question.
Wrong. Okay. Indeed. Yes, and you can do more than that. You can do it all from one fibre. And this is a little bit more experimental. So yes, you can put DTS, DSS, and DAS all on the same fibre, and there are companies that have started to look at building that into the same box. Again, that's whether it's a viable thing. Do you just put 3 boxes with a multiplexer, or do you build it all into one? But there's nothing to stop you doing it all at the same time.
Okay, thanks, Alan. Okay, next presentation is from John Bosley, Engagement Director.
Okay, so we've talked a lot about cable protection. We're here to talk about submarine cables overall. It's certainly a hot topic at the moment. But we wanted to look at how the industry organises itself and how the organisations exist around the world to support cable protection and resilience, and what those organisations are. So the Cable Damage Committee, as a bit of background and history, was formed in 1958 to protect submarine cables, and the name was changed in 1967 to the International Cable Protection Committee to give a bit more of a positive direction rather than talking about damage, to refer instead to protecting proactively. We've got meeting records dating back to 1945, which was prior to the establishment of the organisation. And the topics which were discussed in those minutes were trawl designs, ship anchors, typical causes of damage, so things don't change too much over time. And then there's regional organisations, sometimes referred to as a CPC or a Cable Protection Committee. And I will go through some of the acronyms later on. So ESCA, we're here as ESCA today, was formed as the UK CPC, which was the United Kingdom Cable Protection Committee, in 1999. It then became Subsea Cables UK, but then became ESCA in 2016 to reflect some of the European members and European activities, such as supporting the work of the OSPAR Commission. NASCA is the North American Submarine Cables Association, which was formed in 2000, and then the DKCPC is the Danish Cable Protection Committee, formed in 1998. I'll go a little bit more into what they do. Sorry for the animation. I'm not sure what I've done there. OSCA, the Oceania Submarine Cable Association, is then covering Oceania. So we take a look back at some of the minutes, and we talked a bit about cable charting and the importance of charting. And this is taken from an extract of the Cable Damage Committee meeting on the 27th of October in 1960. And one of the problems facing the committee was that cables were being damaged because it wasn't permitted to chart cables in some certain jurisdictions. So and that was from a security or defence angle. So I won't read it out, but effectively, all of the cable owners had sought permission from their defence authorities to chart submarine cables because of the question, do we keep the locations secret and keep them safe from those who might go to seek them, or do we tell people where the locations of cables are to make sure that they can stay away and avoid them, not fish over them, hopefully not snag them with anchors and so on. So then to give a bit of background to the International Cable Protection Committee, which is the global organisation, I won't read out the mission and the vision, but effectively the ICPC is the world's leading organisation promoting submarine cable protection and resilience around the world. And the regional cable protection committees then have a slightly different purpose to look on a regional basis, whereas ICPC takes a global view. So, for example, they look at the forthcoming BBNJ treaty ratification, work with the ISA on things like deep seabed mining, and has official observer status at the United Nations as well. There's over 230 members across 70 countries, and that consists of cable owners, government, observer members, other marine industries, and collaborates with international organisations, NGOs as well, and supports peer-reviewed research. Mike Clare is the marine scientific advisor for the ICPC, and then there's a legal advisor, Kent Bressie, who looks at international law and UNCLOS. The ICPC publishes recommendations on industry good practices, provides environment updates, and publishes government best practices for cable resilience as well. Then on a regional basis, I've got the terrible animation, apologies for that. So in European and surrounding waters, we have the European Subsea Cables Association. Hopefully everybody is familiar, attending our session here today. Then in North America, there's the North American Submarine Cable Association, which publishes cable charts in a similar way to the KISS-ORCA project, which was described by Peter Jameson earlier. Then the Danish Cable Protection Committee is covering Denmark and the Baltic. And each of the organisations represents a slightly different sectoral representation. So ESCA has telecommunications cables, power cables, and cables for offshore renewables within the membership. NASCA is purely telecommunications cables. The DKCPC has telecoms, power, renewables, and pipelines. So they're separate organisations, but covering the interests on a regional basis. OSCA is telecoms and power, and then there's other regional initiatives emerging as well across Brazil, Southeast Asia, and Africa. So this just gives a general overview of where the regional committees exist, with ICPC as the global body. And I say exist, so the locations with logos shows existing organisations, whereas Brazil, ASCON in Nigeria, and some of the emerging initiatives in South Africa are still in formation. Acronyms, we have the European Subsea Cables Association, the North American Submarine Cable Association, Danish Cable Protection Committee, Oceania Submarine Cable Association, and the International Cable Protection Committee. But we certainly are an industry of acronyms. Thank you very much.
Okay. Okay, presentation from Michael Logan, Mertec Marine, on cable recovery.
Okay. So thanks for your introduction. So I'm Michael Logan from Mertec Marine. We do, I think we're one of the first commercial cable recovery companies out there. We actually started purely by chance. I happened to be a South African farmer walking along the beach, saw some cable that had been recovered for repair, and thought, there's a lot of copper in there. That looks quite exciting. I think his eyes lit up thinking, I can make money out of this somehow. So that was about 30 years ago. I think he spent about 10 years working out how he could strip the cable down, get the copper out, and worked out, you know, there's a lot of cable under the sea, and how does he go about doing that? I think, to be honest, just he'd known how hard those 10 years would be. We probably wouldn't be here today, because it is quite a challenge. So you can see from a picture of our vessel, it's a lot smaller than your typical installation vessel. So installation vessels with the ROVs, DPs, quite expensive, and it just wouldn't be viable to pick up cable to recover and recycle. So we've got freighter vessels that have been converted to recover cable and have about 3 to 4 tanks on it, depending on the size. And they typically recover about 1,500 kilometers of lightweight cable, and a larger one's about 3,500 kilometers of lightweight cable. Just to give you an idea of how recovery works for us, so we, I think that's a nice video that was shown earlier, but we do a cutting run, which will cut the cable, and then we'll go back and do a holding run. I think I've got, there's a picture of the cutting run there, and a grapple there with the all the hooks you can see that will grab the cable, and then away we go recovering. As you heard in the earlier presentation, you have to be careful with the tensions when you're recovering. Of course, we don't really worry about so much about the bending radiuses of the cable, or if there's some damage to the cable, because we're just recycling it extracting the products to put it back into the commodity, clearing routes for new systems to go in, and general decongestion. So, there's a lot of cables that have gone in over the 150 years. So eventually, we're going to get a bit congested, and in some places, that's already the case. So here you can see we've had a successful holding run. Actually, it's probably a bad example to show you. We actually hooked it at the top of the grapple on a random bolt, but it was successful. So you can see it being recovered onto our vessel. And here's just an example of the cable tanks. This is recovered cable, lightweight. I think it was Subsea off of the west coast of South Africa. And as you can see from the pictures, it comes up almost as if it's brand new, which is quite typical in the deep water. In territorial water, it can be quite different because you've got a lot more marine growth. But certainly in the deep water, it's brand new. And if you didn't know about cable, you think, that could be reused and put back in as if it's brand new. And of course it can, but it's not degraded or old. Hopefully this. Sorry about the music, but this is just a picture of a vessel. As you can see, it's recovering. It's just a short video there. So this is another example of where we've done cable recovery in territorial waters. This is actually off the coast of California, recovering, I think, the China-US system. Getting permits here is quite difficult. I think you've probably heard about it in earlier presentations, but this is one of the harder places to recover cable. Every jurisdiction is different. This particular one didn't really care about the ICPC rules of 3 times or 5 times water depth. They wanted the cable originally to be recovered from underneath existing systems. And we sort of said, hang on a minute, that's probably not the best idea. So eventually they settled that we had to get as close as possible with an ROV to cut the cable. And I think here you'll see there's a bit more marine life on the cable. Eventually. Nice example of a suspension there. So what the ROV was doing there was it would cut the cable and then pass it to our recovery vessel, which would go on to recover to the next cutting position. And as you can imagine, in that kind of area, there's a lot of cuts that had to be made because there's a lot of cables coming into specified areas. So that's one of the harder bits. Is a hard bit is getting the cable from the sea, and then what happens after that. So we've got 2 factories, but this is a factory in Port Elizabeth, South Africa, where the cable is transported, and this is where all the recycling takes place. You can see in the bottom right picture, we've got cable that's been bundled up. Again, it looks like new cable, except I think most people will be unhappy about the tight bending radiuses there because the fibers are all broken. So yeah, we transport it to a factory in South Africa, and here's an example of what a cable recycling factory would look like. This is our one. And you can see here we stripped the cable. So if you've ever been lucky enough to go to see cable being manufactured, we kind of do it in the opposite way. It's all pretty much mechanical, stripping the polythene off, steel wires, copper and things like that. And here's some examples of products that are made. So it goes back into circular economy. We, you know, a lot of it's in South Africa. We've got steel cable, wire rope there. A lot of, if you're ever in the vineyards, a lot of the cable going around the fencing is made from different recycled cables, steel wires. It's quite good for fencing, keeping cattle in, and for the vineyards for the hooks. And there's just some pictures of repeaters there. I don't know what quad bike's doing, but yeah, there's these examples of how it looks afterwards. So thank you. Any questions? One question.
What percentage of cable is full?
It's about 97%-ish. We pretty much can recycle everything. The fibre itself's a bit difficult to do anything with. We've had like art projects where they've used it and things like that. We get a bit inventive, but yeah, I mean, that's one of the challenges. The bitumen can also be a bit difficult, but that's used a lot for the roads in South Africa to pack the material. So we found a use for that, but then you do get like bits of mess and stuff that's just not recyclable.
Thanks, Michael. Okay, next presentation is on recycling, reuse, and sustainability from Dr. Mike Clare.
Me again, sorry. I haven't got any powerful walk-on music. I really like that. Yes, I think we'll probably start to take things full circle. I gave a presentation yesterday talking about the need for collaboration and evidence base. And this presentation will aim to try and explain some of that and how that relates to cable recycling, decommissioning of cables, and I guess some more broad thoughts on sustainability and future directions. So Michael's given a really good presentation and background for what actually happens during recovery and recycling operations. I'll talk a bit more about the drivers for recovery and recycling, what happens when cables come to the end of their life. And there've been lots of presentations. Peter started the day off yesterday talking about the length of cables that currently span the global ocean that provide connection through fibre optic cables. But there have been other legacy systems. Examples are out. There's a nice one from Valencia Island on the table from 1856. And so there's a huge amount of cable that continues to exist on the seafloor. There are recovery companies, Michael's amongst those, that have been recovering cables, but there's a significant amount of cable that's still out there on the seafloor. We talked yesterday about how the fact that these cables have a small footprint, there's limited degradation of modern fibre optic cables. So I guess historically the approach has been taken to say, well, there's minimal impact on the environment, we leave it there. But increasingly there are drivers to consider recovering, potentially recycling or repurposing cables of all these different types. So what are those drivers? I guess one of them, and something that is the frame of this presentation, is around kind of commitment to sustainable use of the oceans and thinking about maybe not a complete circular economy, as maybe there are instances. Rob gave a nice example of repurposing cables, maybe taking out an old cable system, repurposing it as a festoon type system to connect between islands. In that case, I guess we're looking at a truly circular economy. But in the case where the materials are not being reused for cables, it's more of a kind of zero waste economy. So there are opportunities and there are drivers, but I think probably the bigger drivers were explained by the weight of presentations yesterday, looking at spatial squeeze, challenges in marine spatial planning. So, just taking the UK as an example of pulling up some Crown Estate and other publicly available data sets. This is from a study led by Izzy Yo here. Looks at the challenges of use of the seafloor and where do you identify opportunities for new cable routes. And one of the opportunities is by removing existing cables and making the most of what are known to be good and resilient routes. There are commercial drivers. There are companies that now exist for recovering and recycling cables. And there are regulatory drivers in certain places in the world. There's a mandate to recover cables after they have reached the end of their engineering life. So many different drivers. One question I guess that I've been looking at over the past couple of years has been trying to look at the potential impacts of cable recovery activities. There are peer-reviewed studies from a field, conceptual modelling basis to look at the impacts from an installation perspective. But to date, there haven't been any peer-reviewed studies which have actually focused on what impacts are involved when you recover a cable. And so this is a gap. This is an evidence gap that needs to be filled in order to inform decision making. I mean, John has talked many times about how things typically have been done on a case-by-case basis, but as you look at the scale of subsea cable networks off the UK and indeed in other places, there's a need maybe for something that is purely generic guidance, but is more nuanced and isn't just looking on a case-by-case basis. So to do that, we need data in order to inform decision making. So these slides just provide some of the potential impacts. Obviously, the recovery of a cable is going to be less impactful than the initial installation, and the impacts are going to be different as to whether that cable was surface laid or whether it was buried. Michael showed some nice examples of grapnel runs which are used to recover the cable, and so you see some of those grapnels and grapnel chains at the top right, relatively small devices which might disturb, depending on the nature of the seafloor substrate, down to about 0.5 metre, maybe in max case 80 centimetres. But these will be relatively short grapnel runs, so a small area of seafloor that's disturbed. And the depth of that disturbance will very much depend on the type and strength of the seafloor substrate. In terms of cables that are buried, it will be difficult to pull up some cables if they're buried, beyond about 1 metre or thereabouts 2 metres. And so when cables are pulled out from the seafloor, there will potentially be some disturbance of that seafloor substrate. But ROV footage, diver video shown in the cases that at least I've observed, this is very, very localized. It's short-lived, and there isn't a significant sediment plume that's created. There would be, were you to use a controlled flow or mass flow excavator, but that is not used. And in those instances, cables are not recovered and they're left as they are. And I think that's important. Because that would basically have a significant intrusive impact on the seabed environment. So the conclusions from the reports and the studies that we've looked at to date are, there are some impacts, but they're very, very localized, and they tend to be very short-lived. When I started looking at this, I guess 5 or 6 years ago, I was shown this photo on the right-hand side, G, which is a cable, I think, from the Mediterranean, from relatively shallow water. It's almost entirely encrusted by corals. And all sorts of benthic fauna. I'd seen examples of photos in F on the right from offshore California, where we have anemones and other organisms that like to plant themselves on cables. And people had chosen, I guess, to show these photos because it looks quite charismatic. It looks like cables and biology are existing in harmony together. However, there are a number of questions. If you introduce a cable, you introduce a new substrate. So are you introducing different organisms that are not endemic? So the question I'd asked and a number of other people had asked is, how representative are these examples on the right-hand side versus what we see on the left-hand side that Michael had shown, where cables have been recovered after 30, 40 or 50 years on the seafloor, and they appear to be coming up clean and pristine. And the answer from the studies and from the cable recovery reports that have been looked at, and this includes several thousand kilometres worth of cable being recovered, is that on the left-hand side, this lack of colonisation, these clean, intact cables, is the norm, and on the right-hand side is the exception. And we can explain why they're happening in these places. It's where cables are surface laid in relatively warm environments which are well oxygenated, and those on the left-hand side tend to be in much cooler areas of deeper water with relatively low biodiversity. So most of what we're seeing, and just one example, SES recovered almost 2,000 kilometres worth of cable from the North Atlantic offshore Portugal. And in that, they only found one instance, about a 3-metre long section of cable, where there was any biological colonisation at all, and the rest of it was a clean cable. And I guess if the cables looked like they did in G, then organisation like Michael's probably wouldn't be bothered doing this because their back decks would be full of bits of coral and other stuff. There is a lot of value, however, in systematically recording biology during recovery. There was a paper written in the journal Nature in, I think, 1872, which said it would be really valuable to send biologists or scientists on cable repair vessels because they could record that sort of information. We're now starting to do that, so hopefully things kind of move pace a bit further. But we can learn all sorts of insights into, the biology in the deep sea as a result of these recovery operations. Because headline findings is what we've seen is recovery generally has a very minor environmental impact. But also the environmental impacts of leaving fibre optic cables on the seafloor will also be minor. So this does need to be considered against a whole range of different considerations. If there's a mandate to recover cables, it's worth making or being aware that it will not always be possible to recover all lengths of cable. In some cases, excess burial has occurred, so cables will be buried to a depth which will inhibit the recovery using typical approaches. In some cases, the migration of sand waves has created 5 meters additional sediment on top of the cable after it was installed, and that would also inhibit recovery. And there will be places where there are cable crossings, there are physical protective structures which have been placed. So it will mean that sections of cable will have to be cut and clump weights will have to be placed such that those sections of cable will remain in place. And various other considerations might warrant leaving cables in place. For example, if a cable was laid through an area many decades ago, which is now designated as a particularly valuable area for seafloor habitats, maybe considerations will need to be there. So I have a statement that a case-by-case approach is needed, but I think progressively building an evidence base will help make sure that it's not just a generic approach, that there are, scenario-by-scenario approaches. And so the presentation by Indexima gave a really nice overview of some of the approaches that are happening. Can you all hear that? That's lovely, isn't it? It's a blue whale from offshore Oregon that was recorded on a fibre optic cable. Why I'm talking about this is because there are other opportunities for out-of-service cables. And so one of these opportunities is the use of cables that are maybe no longer used for data transmission to be used for scientific observations. And so we can make all sorts of kind of annoying. Or she, I don't know in that case, but it's been possible in some of these studies offshore Svalbard to identify the sex as well as the species of whale and to work out whether it's a mating call or whether it's a feeding call. So super exciting, and you can repurpose cables potentially into kind of a series of hydrophones to listen to all sorts of different noises in the ocean. And we increasingly recognize the ocean is a very noisy place, but it's noisy because of a whole heap of different things, because of human activities, vessel traffic, of whales and cetaceans and other organisms. Shrimp make choruses when they sing in submarine canyons. But we can also hear and detect other things. So we can look at temperature changes from things like distributed temperature sensing and record tidal fluctuations in seafloor currents and ocean mixing. We can use changes in the phase of the signal that's recorded to not just detect seafloor currents, but their intensity and their direction relative to a cable. We can record earthquakes and volcanic processes, which will be really useful for early warning systems. So lots of opportunities and lots of opportunities to continue learning about the ocean through cables. So I guess this is one of the other possible opportunities around decommissioned cables and contributes to a better understanding of the ocean, which covers 71% of our planet. So there's no one solution there. I think this is why we need to have this holistic view of sustainability, and indeed what we do here at the Oceanography Centre is to try and take a holistic view of the ocean as well. When we're thinking about sustainability, I think it's really important. I think some people just think about carbon emissions and carbon offsetting, but it's a much bigger picture. And some of these things, disturbance of a seafloor habitat, in many cases quite hard to put a quantitative number on. So we need to be thinking about all of these different aspects. And if we do change something in one way, what are the potential adverse implications that could exist? So this comes through to thinking about, say, the selection of materials for cable physical protection. I think something that is important that all of us are thinking about are where the knowledge gaps are, what the issues of not having them, as in what evidence base is missing, and how does that inhibit us from making sound decisions. So collectively to work out what those knowledge gaps are, to share them, because my experience has been, as soon as I said, we don't know this, people across ESCA and the ICPC have been very keen to say, well, we have data, why don't you look at it? And so I've really appreciated that over the past few years, the willingness of this industry to share data so we can push forward our scientific understanding and our understanding of the ocean. To form an evidence base for organisations like OSPAR, the United Nations, and for local regulators, a peer-reviewed evidence base is absolutely critical, and we need data for that. So that sharing, the input of those data, liaison across academic research, industry and policymakers, particularly through things like these events, I think is very important, and it will become even more important as we start looking towards initiatives like marine net gain. So to say that we are going to leave the environment in a better condition than which we found it. What does that look like in practice? I think there's going to be a lot of questions, but the suggestion is this should be an industry-led initiative because the industry best understands the approaches and what might work. But in some of these instances, we're in quite kind of an experimental phase. So I think it would be very interesting to see where those discussions go and what the different solutions look like going forwards. So I think that's all from my side of things. I also wanted to say a big thank you to ESCA, to the Crown Estate Scotland, for bringing so many people here, because the discussions we've had, certainly I have had, Izzy has had over the past few days have been really, really useful. And I hope that they keep going on into the future. And yeah, it's been fabulous. Thanks very much, Clive and John, as well, for all of your hard work.
Thank you, Mike. Yeah, sadly, that's the end of the workshop. I've got a few little things to say. In terms of feedback on the event, you just use Slido again. There's a section on Slido. You can submit your feedback, and we'd be very grateful if you could do that. Because obviously, it's a lessons learned exercise, and we plan to hold the event every year. And so it'd be good to have that feedback. For the actual event, it will be streamed on YouTube if you want to listen to it back. It'll only be there for 7 days. So I think, Claire, you're going to put the link out tonight or tomorrow. So yeah, look out for the link. And but again, it'll only be there for 7 days. I've got thanks as well to Mike and also Alice for their fantastic support, and Izzy as well. Thank you. To the Crown Estate, Alice, thank you for your support, and also from Crown Estate Scotland, Rona. ICPC, Suboptic for their great sponsorship prizes. And that's about it. But I'm sure you'll agree it's been a great event. Hope you all enjoyed it. As I said, we'll do another one next year. But keep in touch with ESCA, please, for the bulletin. And if there's any non-members that want to look into the work of ESCA and even consider joining, then obviously just contact me or visit the contact page on the website, and obviously send you some more information. But yeah, a great event. So thanks all for coming. There will be lunch now for those attending the Next Gen networking session this afternoon. I think that's going to be served at 12:45. That'll be served outside. So have a safe travel back for those not attended this afternoon, and hopefully see you next year. Okay, thank you. Thanks, Mike.
We'll leave that up.
Here, but I'll just shut the Zoom down.
There's some commercial